Okay, so hi all. Okay. So in this video, we'll finish up our we finished our derivation of the solution to the heat equation, but I'll do a simple example of solving the heat equation that hopefully will a little bit illuminate the what is this, right, or what is this thing that we're looking at. And then we'll get to, mostly in this video, our main strategy for tackling more general heat equation and wave equation, which is what we'll do next week, problems for which we need a new tool, right, as sort of a whole new kind of thing, which, well, we'll get to that. But so just a reminder of our I think this is the last slide. Yep, the last slide from last time. I'm not going to do a whole big review because obviously that was a long derivation in the first place. But let's stare at this conclusion here, so that we can make a little bit of sense of this before we try one. So we ended up with a solution to the heat equation, given, or in fact, the general solution. We ended up with a whole bunch of solutions. So these guys up here at the top, these UNs. These are each of those is a solution, right? Where n is just n are just the whole numbers, 1, 2, 3, and so on. So all of those via our big derivation, all of those worked. So just like we have seen time and time again in ODEs or DEs in general here, we get a whole bunch of solutions. Now, for a first order ODE, we get one solution. For a second order ODE, we get two solutions. Now, for a PDE, I mean, the order of these is not high. It's a second order PDE because I have a UXX term. But maybe you have some appreciation for the idea that since this is a function of two variables, right, u of x and t, that it should hopefully make sense that actually I may have far more than just one or two solutions. And in fact, as we proved, we derived this bad boy here. Those are actually all solutions to the PDE. And so much like we have done time and time again in our year of differential equation solving, if you have more than one solution, if you have a collection of solutions, then any, as we would call them, linear combination is also a solution. So that's how I don't know whether I said this at the end of the last video, since I said I was just happy to be done with this monstrosity. But since all of these, or each of these, is a solution up here at the top, if you take any combination, that's me adding them up here, any combination of these, same thing, I just copied the same thing down again, would also be a solution. Okay, this is a homogeneous PDE. I don't have any external terms that aren't, I just have a UXX and a UT term. So just like we've done many, many other times, if we throw together any number, right, Cn, of course, is a constant, any number of any of these would form a solution. So this is the general solution. So of course, how do we get to a specific solution, right? Or I have a real problem in front of me, and I want to know, well, specifically tell me what the solution is to this one specific heat diffusion problem. So this represents the general solution. And this, I mean, again, right, I'm going to just say this so that you don't feel awkward if you feel this way. I mean, yes, this is a beast of a solution. But it's, I mean, while, yes, there's a lot going on here, just try to remember, and we'll see this in the example we're about to do, this is just a sine function. I know I got this n pi l thing, and I'm not too excited about that. And oh my gosh, and I have all these letters here. I'm not too excited about that either. But what it is, actually, just squint at this for a minute with me. This is just e, that's a number. I don't know what it is. That's some crazy number there. T, right? So this is just our old friend, e to the t, with some coefficient, and sine of x. Now, usually we'd only have one variable, so we've done many times, or many solutions to problems that have looked like e to the something t with trig, right? We've seen that in ODEs time and time again. So in many ways, this is similar, right? I guess I want to just have you at least acknowledge that we've seen e paired with trig pretty much all year in differential equations in general. Now, the big difference here is that, of course, the E is based on time, whereas the sign is based on location. Remember, T is time, X is space or location on the bar. So this is obviously different in the sense that I have two different variables, but it is still kind of a familiar character is what I'm trying to at least impress upon you. Okay? So how do we get at this is a general solution. So how do we get at a specific solution for a specific problem? Well, notice, sorry, that was just one last thing here, right? So how would this is obviously super general because I have I'm adding up infinite number of these. Remember, alpha, pi, and L, and N, because N is whatever. These are known. So that's known, those are known. The only thing I don't know here is what are these CNs? What are these coefficients? Just like any other ODE that we've solved, or any DE we've solved, we get a general solution that has C1, C2. This happens to have C1, 2, 3, 4, 5, all the way to infinity. Okay, but right. And then I have to do something at the end, after I get my general solution, to find the constants. So I want to do the same thing here. So the cute trick that we're going to employ here in order to figure out who are the CNs, because that's always how I go from a general to a specific solution, is to say, I'm going to just point because I have it here in front of me. If I plugged in t equals 0, which, by the way, is that not what we always do at the end of a general solution, is we plug in times 0, and then we use the initial values we have to solve for the constants. Well, what would happen if I plugged in times 0? Well, that would kill that term. Right? That term would just be 1. So I'd be left with that. All right, so I'm going to say that on the next slide, but I wanted to point it out here on this one. So just like we did, just like we've always done with DEs, notice that if we plug in time equal to 0, our general solution, that big monster, becomes a little simpler, right? U of x, if we plug in 0 for t, and this big sum here, so we have Cn. Now that E term, I'll just do it here as a fancy 1. Turns into just 1, because you get e to the 0. So that's 1, obviously. And then you still have the sign thing. Okay? Right, so we'd at least get that. Now, this certainly doesn't immediately tell me what any of the CNs are. But at least this gets me close. Now, what is this, right? U of x and 0. Remember from our earlier notation, that's what we've been calling, or that's what we were calling f of x. That's right, both of these are the initial, what we've been calling boundary condition. Right? Or in other words, the temperatures across the rod, or the bar, at time 0. And remember, we have that. That's how when we were framing this question, we said that's one of the things I'm going to have to be told in a problem, is I'm going to have to be told, tell me about how the temperatures look, or what's the temperature profile at the start of the experiment. That's obviously time 0. So what this is saying here, at the very least, I'll just write this in words here, is that the initial boundary conditions, which we've been denoting in our problems little f of x, is going to help us, not just help us, it will do it for us, but I'll say help us compute the constants, which are these CNs. Okay? And that's because of this, right? Now, that doesn't tell me right off the bat, oh, so C1 is 1, and C2 is 5, and C3 is -3. Okay, right, so this is good news, but not a home run yet, right? This is like I have an idea. This has to work, so what I wrote down up here, the star, is true. I'm not quite sure how to use that just yet. And that's going to be our big tool that we're going to learn, known as Fourier coefficients or Fourier series. But let's do an easy one for which I'm actually going to just, star is going to be enough to get us an answer, right? So let's try, because I'm desperate at least to actually do a problem here rather than most of all of last week's stuff was just getting ready. And I'll be honest, and maybe I said this last week too. Sure, I mean, solving these in real life is usually done via computer program and not so much by hand. And even when we get our better by hand solution thing, it's still going to probably be a little bit of a bear to do anything that's difficult by hand. So in practice, people solve these with programs, right? MATLAB or something like that. And so, what am I going to have you do in homework and on exams is more of the discussion of how does this come to be and sort of almost more of a theoretical, the ideas behind this, rather than doing examples. But there will be some examples, right? And here's one. So, so let me state this for you here. So suppose, so you have a bar of length 2, whatever's, meters, whatever you want, and the initial temperature is given by f of x, which is 3 sine of 2 pi x. And of course, in case it's not clear, right, x, remember x, that's our bar. Our x is of length 2, so x is range between 0 and 2. And of course, when we say initial temperature, of course, describing the temperature at time 0. Okay, so that's this f of x that we've been talking about, the initial boundary condition. So the question then is, predict the heat, right? So question. So predict the heat across the bar at time t. In other words, solve the PDE to get the equation for the temperature profile, I guess, or the temperature across the bar at time t. All right, so before we get to the solving, which is going to be easy actually for this example, let me at least get us a picture of what are we talking about here, right? What does this problem even say, so that we can make sense of whether our answer, when we get it in a few minutes, does that even make sense? Okay, right. So I'm just going to draw a graph here, and I'm going to add to the graph as we kind of do our solution here. So I'm going to get this all on one big graph here. So this is x. So if we do graphs, usually, this is always the x-axis, right? So of course we'll do that as x. On the y-axis, or what we would normally have called the y-axis, is where you're going to put u, which of course is temperature, right? So just remind yourself. U, which is our big mystery function, that's temperature. So we're going to put that on the vertical axis. And then what to do about t? Well, obviously, I mean, nobody wants to see this, right? This gives you bad memories to Calc 3 probably, right? So we're not going to do a 3D graph because it's just a shit show. But a cute way to show a 3D thing without having to ever do a 3D graph is to just draw several regular, and by regular I mean 2D graphs. So a cute way to show solutions, and if you're doing this for a senior thesis or any sort of project where you're solving or describing PDEs, you're going to usually just see graphs like we're about to draw, which is this is just a regular old graph that I'm about to draw, but just draw it in for several times. You know, t equals 0, t equals a half, t equals 1, whatever, right? Because, of course, in the human world, that's you drawing the evolution of the, in this case, temperature profile over time. So right now, I don't know much about the temperature profile, but I do know that it tells me initially it's given by this f of x function. I know what the graph of that looks like, and if you don't know, you could always punch that into a calculator, but we are all smart people here. We know what a sine graph looks like. It's a wave. Don't let the 2 pi here concern you, right? So as x goes from 0 to 2, as x goes from 0 to 2, this is going to go from 0 to 4 pi. So I don't think it's a lot to ask junior and senior math majors to be aware of the fact that sine, of course, repeats itself every 2 pi units, or every 2 pi, cycles, I guess, right? So sine repeats every 2 pi. So as I graph this thing, whether you have to use a calculator or just use your brain a little bit here, when I go from 0 to 1, when x goes from 0 to 1, that's here, this is simply going to range from 0 to 2 pi. Well, that's one full cycle of sine. And now, what does this 3 in front do? It just means the amplitude is 3. So rather than just going between 1 and negative 1, this is going to go between 3 and negative 3. Okay, so hopefully all signs are pointing, no pun intended, all signs are pointing to this being, oh boy, okay, that looks good so far. That was pretty good, actually. Okay, so that's one complete sine rotation, I guess. And then what happens between 1 and 2, it just does the same thing, right? When x is 1, this is 2 pi. When x is 2, this is 4 pi. But we know that sine and cosine both are periodic and repeat every 2 pi units anyway. So I'm just going to get the same exact graph again. So I'll try to duplicate. Oop. All right, not bad. Actually, I'm going to cheat here. This looked like it was going to head up there, so that's officially now too. Okay, so all right, not my best, not my worst work. So this is the initial temperature. So here I'm going to label this, somewhere on here. T equals 0. It's probably not a great place. Oh, whatever. Okay, I will. I'm going to do this in different colors anyway. So that's the initial temperature across the bar. Remember, the bar is, I'm going to erase this, but, ooh, gosh. The bar is literally sitting right there. So, I can't, I just got to get rid of that. Right, so this is telling you, as I go from left to right, the bar that's literally sitting on the x-axis right here, it's hot right there, really cold right there, really hot right there, really cold right there, and in between it's whatever, medium or something. I don't know what you want to right? So it's the cold, you know what I'm saying, right? This is just a temperature graph. So I don't know, we could tell a little story that says something like, this bar, there was fire here, there was ice cubes here, something like that. And then whatever, in between it just sort of is its natural temperature. All right, so it's possible, right? It's possible that whatever this experiment, you did this sort of heat up some of it, cool down some of the rest of it, and then we say, go. We turn off the heat, we remove the ice cubes, and we ask ourselves, what happens to the temperature across this bar, which right now is hot, cold, cold. What happens as time goes on? This is at time 0. Now, before we even solve this, as humans, I think we have some idea of what's going to happen to this bar. Remember, the idea is that I'm always imagining that on the ends of the bar and the ambient temperature of the room, or wherever you are with this thing, is 0, which of course is along the x-axis here. So I'm always assuming that 0 is sort of the natural state or the equilibrium or the, right. So of course, as time goes on, I think the hot parts are going to get less hot, and the cold parts are going to get less cold. Right? Again, I don't need a big fancy solution here to know that probably that's what the solution should look like, is that as I go through time, these peaks and valleys should be becoming diminished, I guess. All right, but we're going to come back to this graph, so you have this in your notes. That's time 0. But we wanted a solution. Right, I promised that we'd actually do a real problem here. So, oh, I'm sorry, I left out one thing. So, predict here with, sorry, I forgot to give you the alpha squared, which is the conductivity coefficient, right? So that's the number that's in our ODE, in our PDE. For our example, let's take it to be 1/4, which means that it's a reasonably conductive but not superconductive metal that is heated up and cooled down here. All right, sorry. So that's the other thing you need, of course, to solve this. Okay, so of course our PDE, just to write it down then, is this. Here's our initial temperature. I'll just copy it down here so we can all look at it one more time. That's our temperature. L is 2. I don't know. I think that's about it, right? Those are the essential numbers or quantities from our setup to the problem. So let's cut right to the chase. We know that the general solution is, so here's our big thing. So I can at least fill in some of these things so that I don't have such a monster to look at each time. So I'm just copying our general solution down. So I have alpha here. Alpha is 1/4. Oh, did I mean alpha or alpha squared? That probably doesn't really matter. Okay, well, I went with alpha squared, I guess, right, as being 1/4. So that would mean, of course, that alpha is 1/2. Right? Okay, so that's alpha squared. So alpha is 1/2. N, I don't know how much that is. And pi. L is 2. That whole thing is squared. It's a lot of stuff to write down. But this is me just filling in our general solution and filling in this case, the fact that alpha is 1/2 and L is 2. So that's how I put a 2 down here. And then sine of n pi over L, which is 2x. Okay, so that's me just filling in these two values. Okay, so, all right. Now, how is this supposed to, this is still a whole bunch of stuff. So let's use the fact that I know that at time 0, this has to equal f of x. So, but we know, so using the boundary condition, we get that at time 0, this has to be 3 sine of 2 pi x. And what do I get when I plug in 0 over here for t? Well, of course, this gets blanked out. Well, that becomes 0. But this whole, the e term, just turns into 1. So when I plug in time 0, right, that's what that says, then I just end up with Cn sine of n pi over 2x. Now stare at this for a minute and don't overthink this. On the left-hand side, I have 3 sine of 2 pi x. That's a function. I don't know, it's a sine thing. It's not just any function, it's this one. It's the one we just graphed. Now over here on the right-hand side, I've got infinity sine functions, right? These are all sine of something. Now the only way for these to match, which of course is what that equal sign means, well, how will I make these match? Well, notice one of these is going to match pretty darn nicely with this. Now, what do I mean by that? Well, what's the difference between, right, so what am I looking at over here? This is n equals 1 to infinity. So I'm looking at sine of, if n is 1, I'd have sine of pi over 2x. When n is 2, I'd have 2 pi over 2, also known as pi. I'd have pi x. When n is 3, I've had 3 pi over 2x. When n is 4, I have 4 pi over 2x. Hello, 4 pi over 2. 4 pi over 2 is 2 pi. Oh. Well, look at that. So as it turns out, the fourth term of this infinite sum over here is actually exactly this. Okay? So, right? So, I mean, I'll give you the, C1 sine of pi over 2x, C2 pi x, C3 3 pi over 2x, C4 sine of 2 pi x, and then more. It's infinite. But look at this. How the heck am I going to get this to equal that? Well, how about we do the easiest thing ever? Let's make that 0. Let's make C2 0. Let's make C3 0. Let's make all the other ones, I ran out of space, right? But all the other ones, let's make them all 0. And all I have to do is match this to that. Well, immediately, doesn't that just mean that C4 is 3? And that that's the only one out of this infinite sum that you actually need. All right, so it's a I don't know, I don't want to really call it a trick, but it's a clever thing to do. So, right, so I'm going to say, in order to make, I don't want to erase my arrow, that was a pretty good arrow. Right? So to solve this, we're going to let all the c's equal 0 except C4, which we're going to make 3. Voila! I have officially matched these up perfectly now, what seemed like a very daunting task a few minutes ago. And so if all the CNs are 0, except this one, then this big awful sum is actually not so big and awful after all, because it only has one surviving term, namely the fourth one. Okay? So this maybe seems like a little too good to be true, but it isn't. So I ran out of space here, so let me just put the conclusion here, right? So this is the general solution. That doesn't change, right? That's still the general solution. But if you want the specific solution, so the specific solution for our initial boundary, that's f of x, is, instead of having all of those awful things, I'm just going to have one of them. I'm going to have the n equals 4 term. I'll write it here. I'll give it to you general first, right? So it's C4 E with all of this stuff. Right, so here's my general term. But I'm just going to save the 1. I'm just going to write out the n equals 4 term. where C4 is going to eventually be 3. But but I'm going to fill in n equals 4, because that's the only one I'm saving, right? All the other ones, I'm making the C1, C2, C3, etc. I'm making them all 0. So I don't need to actually write out this term. Why would I? They're all zeros. So the only one that actually survives is the n equals 4 term. So I'm going to fill in n equals 4 here too. So let's see, just so I can preview this and get it right here. So here, right, when I fill in n equals 4, of course I'd have 2 here, and I divide by 2 on the bottom. I think I did that on purpose so that it looked nice. So I'd end up with just 1. Oh, I have a pi here too, right? But when n equals 4, this just turns into pi. So I'd have negative pi squared t. I don't really need a parenthesis actually, just go with that, negative pi squared t. Okay, here, let me remind you, right? We're just doing n equals 4. And then my sine piece. Sine of n pi over 2. And once again, the only one I'm doing is 4. So I'll have 4 pi over 2, also known as 2 pi x. Okay, and then since we just computed this, C4 is 3. So this is actually all I get after all of this craziness. That's the specific solution for our specific rod, or bar, whatever we're calling it. Okay, so let's go back to our picture now. So this is a solution for our specific problem, and it gives us the solution at any location. So if I said, what's the temperature after 2 seconds in the middle of the bar, for example, I could plug in time equals 2, and at the middle of the bar is x equals 1, and I would of course get a number for that. Or what's the time? Okay, right, we could play this game, right? So this is the actual solution to our problem. So I could use this in the usual kinds of ways. But since this works at any time t, let's add some graphs, let's add some curves to our graph from the last slide, or a couple slides ago, so I can show you the evolution over time. So what's happening to this? So as time goes on, what's happening to this? I mean, sine is an oscillator. So as I read, and this has the x in it, right? So as I go from left to right along my bar, I'm still going to have a sine curve graph, an oscillator. But as time goes on, as t gets bigger, that's right here, obviously pi squared is about 10, and I have a negative there. So I have something like e to the negative 10t, let's say. Well, as time goes on, this piece of course goes towards 0. So while sine is going to continue to oscillate, we've seen this before, right? This is an oscillator. However, this number, and the fact that I'm tripling it doesn't mean it's not going to 0, right? The 3 doesn't do much, but right, this is going to eventually drag us down towards 0. So while this is going to continue to oscillate, it's going to oscillate much more quietly as I head through time, since it's being dragged down to 0. So if I go to my graph now, I don't know how much time, I mean, if time is 1, for example, e to the negative, if pi squared is about 10, e to the negative 10t, e to the negative 10 is like 0.0000, I mean, it's already minuscule. So probably this is one where you'd want to probably sketch some pretty small time steps, like time equals 0.1, or probably even less, 0.01, 0.02. So this is an experiment where, the temperature is moving relatively quickly. I don't also know what the time units are, right? Maybe time is like days or something, or hours, so I'm not really sure, jumping in on these problems exactly what the units are. But as time gets bigger, right, the only thing that's going to change about my graph is that this coefficient, as I'll call it, this guy up front here, is going to be heading towards 0. Which makes sense, right? Because we know the temperature across the rod, the bar, will eventually, or is supposed to eventually, settle back to 0. Right? So if I was to, if we take this, right, and if you were again presenting this in some fancy format, and you wanted to say, well, let me draw you a picture, almost like a phase portrait, right, or some sort of a diagram to show the solution to the PDE, you could pick some t's, probably again some pretty small t's, I think, but you could pick some t's and say, all right, let me plug in some t's, and then it's just a regular graph, right? If you did a numerical value for t, this is just a regular graph. So what would those look like? So I did t equals 0 there. I'm just going to make these up, but if I do one in blue here, so at t equals 0, maybe I won't do blue just yet. I'll save that for a colder one. Well, although I have hot and cold here, so I'll do orange next. So what's the difference between t equals 0 and maybe the next time, whatever it is simply you have the same graph. It's just that as you go through time, it's just that the peaks and valleys are becoming less noticeable, or less steep, or whatever you want to say here. All right, so maybe that's, I knew I was going to regret putting t equals 0 there. So let's call that, I don't know. I'm just making up numbers because I have no idea what the next appropriate thing to graph might be, but I'm just going to make something up like t equals 0.1. So sorry, let me put t equals 0 back on here. Okay, so that might be the next one. If I go a little further, as t gets bigger and bigger, I'm going to get an even more decreased or more subtle amplitude. What's it going to be called? And that might be t equals 0.2. Right, okay, and probably it becomes pretty darn close to just flatline 0 pretty quickly, because of course that pi squared is a pretty large number in front of there. Okay, so of course, this isn't that surprising. We already previewed this answer, that we kind of knew, well, yeah. The things that were hot cool down, or the places that were hot. This was a hot spot on the bar, around 1/2. It was quite hot when we started, but over time, that temperature is decreasing. Similarly, right here at 3/4, it was very cold. It's -3. But over time, it's moderating towards 0. So it's warming up, right, towards 0. So, I don't know if this is, sometimes it's a little bit like, well, yeah, we already knew that was going to happen. Sure, we did. But I will say the significance of this, of what we've done here, this is our very first I solved an actual PDE, a real example one. You can't solve this with an ODE. You can solve it sort of in pieces, I guess, with an ODE. But what's special about a PDE is that you've wrapped it all into one. It's somewhat similar to the fact that when we, earlier in the semester, we switched from just solving a single ODE to solving a system of 2 ODEs. It's kind of the same kind of idea here, where I'm graphing, I'm considering these two quantities operating in tandem. Think about predator and prey. Well, this is time and space, which both collectively contribute to the temperature, the heat spread, or the heat diffusion. So there's some similarities here, but this is I'll say impressive, I guess, even though this didn't seem that hard to solve, or this specific example wasn't that hard to solve. But this is big, right? We've actually solved a PDE here. So let's immediately ruin our happiness by pointing out why what we just did It's probably not going to work all the time. In fact, probably will not work most of the time. So how did we actually get to an answer here? Oops, sorry. Is we just here we are. Right, we had this, I don't know what you want to call this double arrow situation here, which seemed pretty darn convenient, didn't it? So you should have a natural question right now, which is something like, yeah, that's nice. And maybe even if I had more than one sign, right, like if my f of x, instead of just being one of these sign kinds of characters, maybe I got a couple of them. Okay, then I save a few of these. All right, that's not too bad either. But of course, the natural question is, what if your initial temperature profile, this little f of x, what if that's not already one of these sign things? What if it's just anything, right? What if it's even just a constant, like that the temperature is 100 across the whole bar? How am I going to do this? I can't. So of course, naturally, the question arises, which is, but how the heck to compute the CNs when f of x is not just one of these sine curves. Right? So in other words, you don't just have something that already kind of somewhat magically, not magically, but automatically lines up pretty well with this expected series that we're developing here. This is infinite sum. If you don't have something that lines up real nice with that, well then how do you make these equal? I'm still going to use this. So I'm still going to use the fact that I know f of x is going to have to line up star. So I'm still going to use star, which says f of x, whatever f of x is, has to line up with these guys. But I'm going to need a better way to figure out the c's rather than just relying on it being the right form. So for that, we need to launch into what, to be honest, is the main computational topic in solving PDEs in general, which is the ability to do Fourier series and Fourier coefficients. So, I wanted to make a new set of notes. That's why I was hesitating here. So let me end this one. So I'll pause that, and let's start a new one. Okay, so Fourier series is a big topic. Maybe you've heard of it, or Fourier transforms, or FFTs, fast Fourier transforms. This is like the method for solving PDEs or doing anything with differential equations beyond just ODE basic kinds of stuff. So obviously, here we are in end of semester. We're going to give this the light treatment of here's some things about these, and of course the story goes on and on and on, and more of a graduate level course where you might learn more about Fourier series and Fourier solutions. But here's an accessible description of this, and enough for us to be able to solve the more general heat equation, and then eventually the wave equation that we'll do later on. So this is going to be overkill for what we need for heat, but that's all right. We'll get it set up anyway. So let me just give you the definition. So we define the Fourier series. So this is just going to be general. This isn't going to be specific to anything that we've just been talking about. So for any function f of x, by the following. So we say f of x is going to be equal to, so if we can take some function, little f of x, we say it has a Fourier series expansion, or its Fourier series is given by the following stuff. So we have some initial term, a0, some number, and then we're going to add up. We usually use m here. instead of n. Basically this is going to look familiar, right? So some coefficient, which we'll call am, times the cosine version of what we've been looking at, which we haven't actually looked at yet. That's going to be part of the wave solution. And then the sine piece of this, that's what we have been looking at recently, is that term. Okay, so if we define the Fourier series, so we define, this is the definition of Fourier series of a function. We say it's, if we can write little f of x as that. Now what the heck is that? So I mean, again, these things tend to be a little crazy, I guess, or a little bit of monsters here. But what is this trying to say? Is that it says, well, okay, you've got some number, a0, and then you've got a bunch of these sine and cosine things. Again, don't worry about the m pi over l things. I mean, yes, those are going to be important later on, but just think about this. This is cosine, this is sine, our old friends, the wavy guys. And you're going to take am, right? Am and bm are just some coefficients of those. Some numbers in front of them. Okay? So if we could write our f of x like this, we would say that this, right, all of this stuff over here, is the Fourier series of f of x. Okay, so if you, I think some of you, not all of you, took numerical analysis, we do power series or Taylor series. Maybe you picked that up somewhere else in a different math class. This is a different version of that, right? So series, just in general, means an infinite sum that adds up to a known function. So this is just a different way of looking at this. So these are the so-called Fourier series, or the Fourier series expansion for f of x. So just some quick notation, since this is a pain to write, as you might imagine. We will immediately use some notation. So this, right, so this, oh sorry. These cosine and sine pieces are just a pain to write, so the usual shorthand is to just do an m subscript. The only difference between any one of these and another one is just what m value am I on? 1, 2, 3, 4, 5, and so on. So we'll just make this notation so we can save a few. So we will denote cosine of mx, or subscript m of x to mean that, and of course similarly sine, same thing. Okay, so just so we don't have to write that every time. So there's some nice properties of this cosine m's and sine m's. And these are just straight up, sort of calculus things here. And we're going to pull this together to come up with our big result probably in the next video. But let me get through the preliminary properties of these guys, the cosine m's and the sine m's. I'm just going to go to the next slide here. So there are two important properties of these. That are going to help us, or that are going to be the reason why these are going to be the thing that unlocks our ability to find these solutions to these PDEs. So one is that they are both periodic, or the adjective or classification is they both experience or have periodicity. So I think we know what period means, but I'm going to give it to you anyway in case it's been a while since we've looked at this. So of course we say a function f of x has period p if f of x plus p equals f of x for any x. Okay, so to say something has period p, whatever number p might be, is simply saying that, oh, okay, every p units, right? So of course the way to think about this is every p units, the function repeats itself. Okay, so of course we know that trig functions, in particular sine and cosine, so in particular, we already know that, just regular sine of x and cosine of x have period 2 pi, right? I think we know that from way back when, that sine and cosine repeat themselves every 2 pi units. Okay, so but how about these cosine m's and sine m's? What's the period of those? So cosine x and sine x by themselves, they repeat every 2 pi units. Or in other words, cosine and sine have the property that whenever you plug something in, if you were to add 2 pi and try to do it again, or evaluate sine and cosine, you get the same thing. So these have sine 2 period. But how about cosine of m and sine of m? And they're the same, so it doesn't really matter. We'll use cosine, I guess. So how about these characters, since we're going to be doing a lot with them? Well, let's see. So I know how much that is, right? So cosine of m, now I will write out what that is. That's cosine, just by definition, our little shorthand here, that's m pi over lx. Right? That's our notation. Well, I know that that's going to be equal if I add 2 pi to what's in the parentheses there, right? So in particular, I'm really trying to figure out, but how much do I need to add to x in order to have this repeat? So I know that if I take this, and if I add 2 pi, I know I'm going to get the same thing. So, but, how do I want to say this? So if I do cosine of right, so if I plug in some unknown period, p, how do I know how much p is sort of the question, right? So my goal is to have that be equal to cosine of just m pi over l. So of course if I do that, I'd have cosine of m pi over lx plus m pi over L P. So this just has to be equal to, so we need this to be equal to 2 pi, because I know it's going to repeat every 2 pi, right? So I know that if that's equal to 2 pi, then I know that this will be just cosine of m pi over lx, which would mean, right, if I connect the dots from end to end, I'll be saying, oh yeah, okay. So when you add p to what you're plugging in, you get the same thing, as long as what I just circled is 2 pi. All right, but if what I just circled is 2 pi, so we insist, space here, let me go to the next slide here. So if we insist that what I just wrote down, 2 pi is m pi over lp, or m pi over l times p, then we can solve for p. If I just move some stuff around here, I think, let's see, I divide by pi, that goes away, I get what? P is 2l over. Okay, so that's the period of cosine m and sine m, right? So that's the period, so is 2L over m. Okay, now why am I torturing you with this? Well, this is just to say, well, all right. Now, of course, we know that m in our summation ranges from 1 to infinity. So, of course, the period of these guys are getting smaller and smaller as m gets bigger and bigger. So, in other words, they're repeating more and more and more often. So, since the period of each of them is 2L over m, and as m gets bigger, the period just gets smaller, that still means they repeat every 2L. So what I'm going to say here, right, is the period of cosine m and sine m is 2L over m. That's true. But then a common period, that's what I wanted to say, sorry, a common period for all of them is 2L. So you have to think about that for a second. I don't want to overly document this, since this is just logic if you think about it, right? But these guys, right, the cosine m repeats every 2L over n. That's what cosine m does. Okay, so, but as m gets bigger, it just means the period gets shorter and shorter. But if I do m periods, I'll be at 2L. So they all repeat every 2L, right? It's sort of like the common factor, or the common period, really, right, is that they all would repeat every 2L units. Now, why is this important? Well, because we're going to have some nice properties of things that are periodic, but we need to know, if I'm going to try to put them all together, it'd be useful if they all have the same period. So this should, right, so this at least says, well, all of these cosine m's, it doesn't even matter what m is. You can always use 2L as the period for any of these cosine m's or sine m things. All right? Okay, so that's important. So let's give that an underline, I guess, or something like that. So what's this? Why is this so important, and what's this business then with periods, and how is this useful? So we have a idea here. Let me write it all down. So for a function f of x with period p, we have a fact that the integral over any interval of length p is the same. Okay, so that's in words. So this is a theorem or an idea, but it's true. And I'll show you why this is true, just using sine and cosine as our example here. But let me read this to you, right? So if you have any function and it's periodic with period p, then if you do an integral over any interval of length p, you will get the same exact result. Now I'm just gonna draw you a picture, and you're gonna immediately be convinced, I think, that this is true. So I'll stick with sine, not that it has to be sine, but just to have a familiar graph in front of us. Oh boy. Okay. So let's say the period. So let's say this is sine. Then the period is 2 pi, which of course are these numbers: 2 pi, 4 pi, 6 pi, and so on. Then what is this saying? This is saying that if you take the integral over any interval of length 2 pi, so that's the right. So in this example, our period is 2 pi. I think you should get the exact same answer. And we actually probably know how much the answer is for this, or shame on you, I guess, if you don't know if you integrated sine from 0 to 2 pi, you'd get 0, right? But But we can see that with the graph, right? If I integrate sine from 0 to 2 pi, that's that plus that. And we know about symmetry and stuff, right? So that's 0. But I could have also integrated, I'm doing green here, I could have also done, I don't know, pi over 2 to 3 pi over 2. That's also 2 pi units. And even just from my picture, can't you tell, I think, that the green is the same as the red? Because what am I doing here? I mean, these are actually literally the same. But right, the left half of this green is the same size as the left half of this red over here. So when you piece it all together, you still get the same thing. And even if I didn't pick something super symmetric, like, I don't know, come way over here. I have no idea what number that is, but I'll just say start here. And if I have to go 2 pi units, that means I'd be doing from there to there. If I add up that, and that, you get the same exact thing that I either did here in red initially or in green. Okay, so anything that's periodic, as long as you integrate, if you integrate a function that's periodic over its full period, whether it's starting at 0, like the red initial graph was, or maybe green, I started some ways in, or purple, I started just at a random spot, as long as you go for a full period, you will get the same answer. Now, you don't always get 0. Now, for sine, for sine, you do get 0. But even if that wasn't 0, right, whatever number each of these integrals were that I shaded in, you would get the same value for all of them. Okay? So this is an important property because we're going to set up a moment here. Some nice cancellations, right? So we're going to want to know that that's true. So that's the main property for periodic functions that's useful, is that it doesn't matter which period you integrate over, they all will give you the same exact answer. Okay? So in particular, right, for sine and for cosine, you get 0 for all of these. So maybe I'll just jot that down at the bottom here. So I'll say in particular, 2. Just regular old sine of x and cosine of x. Sorry, I should just do this with symbols here. That if you do, oh god, I don't have space here. Here, I'll do it this way. If you do any interval of length 2 pi, sine of x, or cosine of x, you'd get 0. Okay, we did sine here, but cosine's the same. I mean, cosine starts up here, but if you do one full period of cosine, you get the same regions that we just highlighted here for sine. So that's one thing. And for these, we're not going to use sine and cosine just as is, but we will use these cosine m's and sine m's. So if I do an integral over any interval of length 2L, remember, we said that the period for all of these guys is 2L, or a common period for all of these would be 2L. So in other words, the period is a period of 2L works for all of them. So if I do any integral over an interval over any interval of length 2L of these cosine m's or these sine m's, these will also be 0. Okay? Well, those will be 0 by themselves, and any sort of combination of these, at the very least, I know I'll get the same thing. All right, so this periodicity properties, these fun, I'll call them fun, they're not fun, but these properties that we get sort of for free from the fact that trig and even our cosine m's and sine m's are periodic is going to help us later simplify some nasty stuff. So that's property 1. Property 2 is I'll just maybe just jot it down and then we'll come back to this in the next video. So that's 1. So 2 is a word that I think we know from linear algebra. Oh gosh, I'm spelling it wrong. Orthogonality. Okay, so these cosine m's and sine m's are periodic, and they're also going to be what we're going to call orthogonal. So let me give you the definition at least of this. So we say two functions are orthogonal on some interval, sorry. Right, some interval a to b. If, when you integrate over that interval a to b, the product of the two, you get 0. So orthogonality is something that you do in linear algebra, which is a means or a way of saying that two vectors or whatever structure you're looking at are distinct, right, or are independent. Sorry, that's a better word for it. So you check for orthogonality in 2 dimensions. Orthogonality just means perpendicular. In higher dimensions, it's the higher dimensional version of perpendicular. But in general in math, right, a way to check if things are orthogonal, check for functions, or if they're orthogonal, is to see what you get when you do this integral. So, like I said, this is sort of a big thing, so I'll save this for the next video. But the cosine m's and sine m's that we're going to use in our Fourier series are periodic, and they're also going to be orthogonal. So they're going to have this property, which is going to ultimately be the thing, believe it or not, that does let us then solve for these coefficients in our Fourier expansions and get at least a way of doing it. The way that we're going to do it is probably going to be not super pleasant, so we'll do some examples. But anyway, so we'll come back with that in the next video. So let's stop this. So right now there are homework problems in WebAssign. I went through to pick some to post, and I mean you can already tell from just the writing that we've been doing, and really last week and this week. I mean, typing these things in is pretty bad. I mean, even just printing them is pretty bad because there's so many letters and so many subscripts and superscripts and all of this exponents and everything. That I mean, I look through to they have some reasonable problems in there, but I think the typing of your solutions in is just going to be pretty god awful. So I'm going to just give you some sort of written problems. The problems that some of which I borrowed from a book, but I'm just going to give you a sort of a document that has some problems in it. And we're at the point of the semester where I don't think anybody's all that excited or interested in doing any more WebAssign assignments, I don't think. So I'm just going to give you some of those, and I'm just going to post solutions to them, and I'm just going to have you do them for practice and check your solutions. This is already awkward enough that we're not together. I'm not going to do distance pencil and paper homework and have you scan those and me grade them and send them back to you. It's just way too many steps at this point. So I will post some. I'll call them practice problems, I guess, instead of homework problems. But I know you're all good people, so I know you'll all actually do them and try them and make sure that you understand how to do these things. But I will post solutions to those so that you can then just check your answers and reconcile if you have any issues or questions. So so those will be up later this week, so that you can actually try these, right? Because I know that without WebAssign, you don't necessarily have a lot of practice with these. So I will give you some, right, so that you do have a decent amount of examples to look at and to work through and to make sure that you're good at doing these things for our exam. So, which I'll send details around about that, but maybe I can't even remember now if I've mentioned in this class or in other classes. Right, so we'll do an exam on the last day of our course, which is that Thursday of the last week. We'll just do an exam number 3 that'll be on this stuff, on the PDE stuff. So same format and same ideas. That I'll post something and that you print it or look at it on your screen and you do your solutions on paper and you scan and submit your solutions. So more details about that later, but and we'll do it on that Thursday. That I think it's the 14th, maybe is that last Thursday. So we have this week, we have next week, and even Tuesday of the following week to get through a few more things here and there. So so I'll be in touch. Look for another video for Thursday's class this week, where again we'll wrap up these properties and do another example or two. And next week we'll do the wave.